had introduced first order logic in the last lecture. So, from this lecture we will start studying the mechanism of inferencing in first order logic. We will see how we can deduce new facts from the existing ones using first order logic. Now, just to do a brief recap, the difference that we saw between propositional logic and first order logic was that in first order logic you can have predicates which have arguments. These arguments can be instantiated with values from a given domain, right, and we can have quantifiers which says that whether there exists a member in the domain which can satisfy the predicate, which is there exists the variable for that predicate, or it could be an universal quantification which says that for all values of the variable x from its domain the predicate is satisfied, right. So, it is the existence of these quantifiers which makes inferencing in first order logic more difficult than that of propositional logic. In propositional logic we saw that we can reduce the inferencing problem to an equivalent SAT problem, a problem of Boolean satisfiability, and we have different Boolean satisfiability solvers which can solve this. But when we go to first order logic, the domains of these variables can be very large and could be potentially infinite also, and therefore it is not so easy to reduce the problem to a SAT instance. So, let us see some basic things that we need to do in first order logic. Firstly, we need to have some basic inference rules. What can we deduce from what? So, the first of this is universal elimination. Universal elimination says, for example, that if we have for all x likes x ice cream, right, then we can substitute x with Einstein and get likes Einstein ice cream. Now, we can do this because we have this for all quantifier here. So, we are given that for all x likes x ice cream. In other words, it says that everyone likes ice cream, and so if we replace x with Einstein, we get likes Einstein ice cream, and we can deduce this from this statement. If this is given to us, then we can always deduce that Einstein also likes ice cream, right. The substitutions will be shown like this. When we have x slash Einstein, it means that we are substituting the variable x with Einstein, right. Then we have a concept of a ground term. I will define this more formally. A ground term is, for the moment, let us say that it is a constant like we have Einstein here, right. It, by a ground term we mean that it will not have any more variables within it. So, there is no further instantiation that you can do on a ground term. The second rule is existential elimination. So, suppose we are given there exists x likes x ice cream, right. Then if we are given a particular person, say Einstein, can we infer that likes Einstein ice cream? No, we can't, because we are given there exists x, but which of these from the domain of x will like ice cream is not known, right. But we can do the following thing. We can replace x by say something like man, provided that man does not appear elsewhere in the knowledge base. So, if it is an entity which does not exist in the knowledge base, then we can actually replace x with man. So, this man here is a ground term. We are not going to further instantiate this, but this is the placeholder for that x which likes ice cream. So, this one says there exists x who likes ice cream. So, we are say okay, let that person who likes ice cream be called man, right. Now, this man is a ground term. So, we do not have any other quantifier before it. But at the same time, it is not one of the people whom we know. because if it is one of the people whom we know, then we do not know whether that person likes ice cream or not.
Sir, there might be some person who is in man and who likes ice cream because he is in man.
If there is a person called man, then we cannot use man here.
Means there is a person with a separate name
Yes.
which is within man.
No,
So
the man is not a set. Man is a ground term. It is one person. Okay. It's like this, that we are told that someone likes ice cream, right. So, we are saying that okay, let that be man, right, and henceforth we will say that man likes ice cream, right. It is also possible that someone else also likes ice cream. Their existence does not prevent us from having more than one person liking, but we are naming this person man just to use man as a ground term in the inference procedure. We will shortly see why this is useful, and when we generalize this thing, we will call this skolemization, or replacing a variable by a skolem function. I will shortly describe that why this becomes useful. The third one is existential introduction. So, if we are given that likes Mona Lisa ice cream, then we can infer that there exists X likes X ice cream. If we are given that Mona Lisa likes ice cream, then we can always say that there is someone who likes ice cream, right. So, in all of these three, the first one is given to us and we can deduce the second one from that. Like for example, we can deduce likes Einstein ice cream from for all X likes X ice cream. We can deduce likes man ice cream from there exists X likes X ice cream, right. And likewise, if we are given that likes Mona Lisa ice cream, then we can deduce there exists X likes X ice cream. Okay. Now, let us first study one example of reasoning in first order logic, and then we will go to the formal way of doing it. So, this is an example which is inspired from the Asterix comics. So, the law says that it is a crime for a Gaul to sell potion formulas to hostile nations. So, this is our first sentence. The second sentence says the country Rome, which is an enemy of Gaul, has acquired some potion formulas, and all of its formulas were sold to it by a druid Traitorix. And then we are given that Traitorix is a Gaul, and the question that we have to solve is that is Traitorix a criminal. So, let us first see that how we translate each of these statements into first order logic, and then we will see how to do the deduction of the final statement from the first three. So, first one is the law says that it is a crime for a Gaul to sell potion formulas to hostile nations. What predicates will we require? Okay. We will use predicates like, okay, let's write them down. Gaul X to indicate that X is a Gaul. Okay, hostile say Z, indicating that Z is a hostile nation. Then we will use potion Y to indicate that Y is a potion, right, and we will also use criminal say X to indicate X is a criminal, right, and we will also have selling, sells this will indicate, let us say X sells Y to Z. So, x, this is going to indicate x sells y to z, where y is a Poisson formula and x is a person and z is a country, is a nation. And I think we will also require owns. So, owns x y, which will indicate x owns y, where x is a Poisson formula, y is a nation, right. Now, let us look at the first statement, which says that the law says that it is a crime for a Gaul to sell Poisson formulas to hostile nations. It is a crime for a Gaul to sell Poisson formulas to hostile nations. So, we can say that Gaul x and Poisson y and sells and if x is a Gaul, y is a Poisson and z is a hostile nation, and x sells y to z, which means that this Gaul sells the Poisson y to the hostile nation z, then implies criminal x, right. Okay. When we write this kind of rules without saying anything here, it will mean that we always have a for all x, for all y, for all z. If there is any existential quantification, we will explicitly write it down, right. So, this is our first sentence, that the law says that it is a crime for a Gaul to sell Poisson formulas to hostile nations. So, if anybody has done that, then it implies that that person is a criminal. Okay. The second sentence says that the country Rome is an enemy of Gaul, right. So, what we should we have for that? Hostile Rome. So, this is our second sentence, that Rome is hostile for Gauls, of course. And then we have that Rome has acquired some Poisson formulas, right. Rome has acquired some Poisson formulas. So, there exists a y such that Poisson y and owns this says that Rome owns some Poisson, right. And then we are given that all of its formulas were sold to it by Druid rhetorics. Okay. So, that means that for all y, which is a Poisson y and owns Rome y, means that this was sold to Rome by rhetorics. So, sells right. So, for all y which is a portion if and which is owned by Rome. So, all portion formulas that are owned by Rome were sold to Rome by Traitorix, right. Finally, we are given that Traitorix is a Gaul. So, Gaul right.
So the second rule is to show that Rome has some work.
Yes, the second one is to show that at least one portion is there, because we are also told that the country Rome, an enemy of Gaul, has acquired some portion formulas, right. So, that set of portion formulas acquired by Rome is non-zero, non-empty, right. And further, all these formulas were sold to it by Traitorix, right. Now, let us see what do we have to deduce. We have to deduce that is Traitorix a criminal. So, the goal that we have is we want to deduce this, and we want to deduce this from this set of formulas. First one is this, right, and then we have this as the second one, this as the third one, this as the fourth one, and this as the fifth one. So, we are trying to see whether 1 through 5 implies this goal G. Okay. So, firstly what we are going to study is, we will try to use modus ponens as we did in propositional logic, which means that we will try to see whether the left hand side is satisfied, and if the left hand side of an implication is satisfied, then we can deduce the right hand side. In an implication of the form A implies B, if A holds, then we can deduce B. So, we will try to go in the same way, and as we had seen previously that there are two ways of doing this. One is forward chaining, where we start from the given set of rules and repeatedly apply them until we arrive at the goal, and the other option is to start with the goal and then go backwards to see that what do we need in order to derive this goal. So, we will study both of these inferencing using simple modus ponens or the extension of modus ponens for propositional logic as we have in first order logic. So, let us see, we want to start, we start with the formula. So, this is forward chaining. We start with there exists y, portion y, and okay. So, now there exists some y. So, what we will do first here is we will eliminate this implication by replacing y with something which does not exist in our knowledge base right now. You remember we did this for that there exists x likes x ice cream and we replaced x by man. So, we will replace this y by, let us say we will replace it by some portion p. So, once we do that, that gives us portion P and owns okay. And then we also have the rule which says portion Y and owns Rome Y implies that cells traitorix Y Rome. Right. Now, if we use these two, now we will do a thing called an unification. We will try to see whether we can use this to match the left hand side of this. Right. In order to do that, we see that we have to substitute this variable y here by p, right, and there is no problem in doing so, because recall that in all of these we have this for all y outside. So, if this holds for all y, then it will also hold for p, right. So, therefore, whenever you have for all, you can always replace the variable by any other ground term of your choice. So, we say that the left hand side of this rule will unify with this one, and that will happen if we substitute this y here with p. So, this is the substitution that we are applying on this, and that is going to unify the left hand sides, and therefore, we can deduce the right hand side, but again when we unify it, when we do the substitution of y by p, we will have to do it on both sides, right. So, therefore, we have deduced that cells traitorix p Rome. So, we have cells right. And further we are given hostile Rome, right, and we are also given Gaul traitorix right, and from here we have portion P, right. So, let us see what do we have. We have portion P, hostile Rome, Gaul traitorix and cells traitorix P Rome, right. Now, then we can use this rule Gaul x portion y cells x y hostile z implies criminal x, but the left hand sides will now have to be unified with these predicates that we have here. So, that means that here x is going to be replaced by traitorix, y is going to be replaced by p and z is going to be replaced by Rome. So, if we do that substitution on the left hand side, then the left hand side matches with what we have here in the knowledge base. We have portion P, we have hostile Rome, we have Gaul traitorix and we have cells traitorix P Rome. So, these 4 facts have already been deduced and are there in the knowledge base. So, they unify with the left hand side of this rule, and it gives us the right hand side again with the same substitution, which means that it gives us criminal traitorix. So, of these, out of these 4 and that rule and the rule 1 that we had, will give us
Sir, how you are unifying with quotient P and one's row P? It only requires quotient P.
here.
Sir, in the unification with the rule 1,
Yes.
only quotient P is required.
No, because see, you need to have Gall X, Quotient Y, Cells X, Y, Z and Hostile Z, all four together to infer criminal X, right. So, if you just put Quotient P here, right, then you do not get that traitor X is a criminal, right. You just get that for all Y X, Gall X and Quotient P for all Z, Cells X, Y, Z and Hostile Z implies criminal X. See, once you instantiate something, that particular quantifier will go, right, but the others will still be there, right. So, you can only deduce criminal traitor X if you have instantiated all of these variables, right, or else if you are, if suppose you replace X with traitor X and then you have to find Y and Z which satisfies quotient Y and cells X, Y, Z, only then you can deduce criminal traitor X. Okay. So, once we have substituted X with traitor X, Y with P and Z with Rome, then we have all these facts in the knowledge base. We have hostile Rome, we have quotient P, we have Gall traitor X and we also have cells traitor X, P, Rome. All these facts were there in the knowledge base when we applied this rule, and we have deduced criminal traitor X. Okay. Now, this is forward chaining. This is where we started from the existing facts and rules in the knowledge base and deduced that traitor X is a criminal. We can do the reverse also. We can start with criminal traitor X and then try to figure out that how to deduce whether this is true or not. So, for that we will start with criminal traitor X and then work backwards. So, let us see how that is going to work. So, we are going to start by saying that okay, my initial goal is to deduce that criminal traitor X. Then we start with this rule. We start with this rule because this is the rule which has criminal traitor X on the right hand side. So, we will now start unifying with the right hand side. So, with the right hand side, if we unify this, then we will see that we can get criminal traitor X provided that we can find a Gall X, a quotient Y, right, provided that we can find a quotient Y and a nation Z such that traitor X has sold a quotient to that nation, right. So, what we need therefore, if we look at this rule, then what we need in order to deduce that criminal traitor X is that we need Gall traitor X, right, we need some quotient Y, we need some hostile Z, and we need cells and this is an AND because we need all of these. We need to solve all of these. So, now we have 4 sub goals. One is Gall traitor X, one is quotient Y, one is hostile Z and cells X, Y, Z. Cells traitor X, Y, Z, that is right. This should be traitor X. cells stator x y z, right. But these sub goals are not independent, because they have this binding which has to be honored. For example, the portion y that you instantiate y with should also be the one which has been sold. If you instantiate this portion y with some p and instantiate this y with some q, then traitor x is not a criminal, because the one which has been sold, right, and the one that you have here are not the same, right. So, there is a binding which is there between these, right. Then once you have this, we will again move backwards. Okay, this is a solved node, because this is given to us, this is there in the knowledge base. So, this is solved, we do not need to do anything about this. But for portion y, we need to do something. We need a portion y which has been sold to this thing, right. So, what we will do is, we will start from this rule now, that cells stator x y Rome can be had, provided that there is that for all y portion y and owns Rome y, right. So, if we have to have this, then again we have two sub goals, one which says portion y, which actually we already have, right, and we need owns Rome y, right. Right. Now, we are going to use this, that there exists y portion y and owns Rome y, right, and we will replace, use existential elimination to replace the y with a p, right. So, the moment we have that, we will have owns Rome p right, and these two are going to have portion p and recall that the moment that we substituted Rome here, right, we will now try to see whether we can instantiate this also with the same this thing, and we indeed find that in the knowledge base we have hostile Rome. So, this is going to be hostile Rome, right. So, with that now we have arrived at the entire set of ground terms. So, this is solved, this is solved, this is solved, and also this is solved, right. So, therefore, we have completed deducing that traitor x is a criminal. Right. We will study backward chaining in a lot more details when we study a language called Prolog, which will start after a few lectures. I will start with Prolog. That is a logic programming language, and there you will see that this backward chaining is the predominant way of doing the computation. Right. Let us now see that what are the important formalisms that are necessary to create a deductive engine out of what we have just now studied. So, we need the generalized modus ponens. What does the generalized modus ponens give us? That if we have atomic sentences like these pi, pi dash and q, where there is a substitution theta such that if you apply that substitution, then pi dash and pi becomes equal for all I. Okay. Let us understand what this means. This is the left hand side of a rule, right? P1 and P2 and Pn. These are all predicates, they have their arguments, right? P1 dash, P2 dash, Pn dash are also predicates which are there in the knowledge base. We know that these are given. So, we are given that P1 dash, P2 dash and Pn dash are all given to us, and we are given this rule that P1 and P2 dot 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 and Pn implies Q. We are trying to see whether we can infer Q from this, whether we can deduce Q from this, right? And we can deduce Q provided that the left side of the rule unifies with what we have. Like what we were doing just now is we were trying to see that whether we were able to see the text, please. Yes, we were seeing that whether we find a goal, a portion, a hostile nation which unifies with x, y and z such that cells x, y, z is also given in the knowledge base. When we have that, then we can deduce this. So, when we have a goal, a portion, a hostile nation and cells x, y, z, like we deduced from forward chaining, we had portion P, hostile Rome, Groll traitor X and cells traitor X P Rome, then we could deduce criminal X. So, therefore, these are our P1 dash, P2 dash, P3 dash etc. and these are our P1, P2, P3 etc. right. And if they can unify with each other, in other words, if there is a substitution of the variables such that the two becomes equal, right. Like for example, if we substitute x with traitor X, then it unifies with Gaul traitor X. If we substitute y with P, then it unifies with portion P. If we substitute z with Rome, then it unifies with hostile Rome, right. So, the complete substitution that we have is x with traitor X and y with P and z with Rome. So, that whole substitution is theta, right. So, if we look here, if you have such a substitution theta which is able to unify pi dash with pi for all I, which means P1 dash with P1, P2 dash with P2 and so on, then we will deduce Q also with that substitution, because recall that when we make a substitution on the left hand side of the rule, we have to make it also on the right hand side of the rule, right. So, that gives us, we are able to deduce Q with the same substitution. Is this clear? Is it clear? Yes or no?
Yes.
Huh? Fine.
In the example, that substitution is traitor X for X.
Yes, in the goal. Yes, in the when we made the substitution of x by traitor X here, we also have to make it here. This also has to be replaced by traitor X, because you see this is a whole formula. So, if you make a substitution of any variable with a ground term, you have to do it uniformly on the formula, because whatever is the x here is also the x here. That is why we have this substitution of Q also by theta. All right. So, what is the important thing here? The important thing here is to deduce how do we do this unification, because this unification of P1 with P1 dash, P2 with P2 dash and Pn with Pn dash is what helps us in using the rule, right. So, we have to be able to formalize a mechanism for doing this unification. Let us look at some examples of this unification. So, the first one is, let us say So, we define this function unify PQ as theta, where substitution of P with that theta. Now, what do I mean by this? P is a formula, theta is a substitution. What kind of substitution is theta? Say x by something, y by something, z by something, like that, right. So, when we apply that substitution on P and when we apply that same substitution on Q, we should get the same predicate. If we are able to get the same formula by doing the substitution, then we say that P and Q are unified by the substitution theta. Is it clear? P is a predicate, Q is a predicate, and the same substitution is able to unify the two or make them equal. Let us see some examples. Suppose we have nose erdos x is one predicate. Nose erdos x. Erdos is the name of a very famous mathematician, and we have nose erdos Gödel, right. Then the unification here is x replaced with Gödel, because if you replace the variable x with Gödel, then these two, this P and this Q, will become identical, right. Now, this example is inspired from the Erdos number. Are you familiar with what is the Erdos number? Yes? Yes. So, the Erdos numbers were very interesting, because Erdos wrote lots of papers, and there are several numbers which indicate how many co-authors he had and how many people published a paper with a co-author of Gödel, of Erdos. So, one of the Erdos numbers is direct co-authors of Erdos. Another Erdos number is the number of people who, or the number of publications where a person's Erdos number is number of publications in which that person was a co-author of Erdos, right. And that number becomes actually, if you go to one or two levels, the number becomes really staggering. Anyway, so let us return to our example. So, let us say that we have nose Erdos x and nose y Gödel, right. Then the unifier is x replaced with Gödel and y replaced with Erdos. Now, see this theta, the substitution is actually replacing one variable of this predicate and another variable of this predicate. But after that substitution is done, then these two becomes identical, because the left hand side will become nose Erdos Gödel, the right hand side will also become nose Erdos Gödel, right. Okay, now, let us go to a few little more complicated example. Suppose we know we have nose Erdos x and nose y father of y. So, every person knows the person's father, right. Now, here the unifier is y with Erdos, and then this is more interesting, x with the father of Erdos, right. Now, see what is this father? It is a function, right. Recall that in first order logic we can have functions also as arguments of predicates. So, then this side will become Erdos father of Erdos, and this side will also become Erdos and father of Erdos, right. And then when does unification fail? It fails in cases like this, that you have nose Erdos x and nose x Gödel. Now, this x is a common variable here, and now there is no way that you can unify these two, or there is no substitution of x which will make this predicate and this predicate identical, right. So, the unifier is empty. Now, the important thing is that we require the most general unifier. And why do we require the most general unifier, and what is the meaning of the most general unifier? The most general unifier means that when we replace a variable with a ground term, right, then we are effectively replacing, we are creating a special instance of that rule and deducing a fact for a very specific person, right. Like if we have for all x likes x ice cream and we replace x with Einstein and put likes Einstein ice cream, well, that is fine, but it also, we must also remember that this is just one of the many special cases of for all x likes x ice cream, because there are every other person who also likes ice cream. The fact that likes Einstein ice cream is fine, but if that is not what we require for our proof, then we could generate a lot of people liking ice cream without actually using the fact, right. Okay. So, when we replace something with a unifier, when we unify something, we will have to see that we unify in the most unrestricted way. The more ground terms that you bring into it, right, you will find that it is that the right hand side will also have more instantiations, and it will be useful for a more restricted set of cases. During some tutorial, I will talk in more details about the most general unifier and how to derive the most general unifier, right. And we will also see that when we use the most general unifier, then the number of steps in your deduction will go down. Did you get an idea about what is meant by the most general unifier? Okay. Right. We will study this in more depth when we study prologue. This is a logic which is a fragment of first order logic. It is called horn logic. And what is a horn logic? Do you remember that when we were studying propositional calculus, I briefly mentioned what are horn sentences. Horn sentences are one where on the left hand side of the rule you can have a conjunction of many predicates, and the right hand side you have a single goal. Now, we do not allow ors of predicates on the left hand side or the right hand side, right. The similar thing applies for first order logic also, and that fragment of first order logic is called horn logic. And in horn logic, the advantage is that you can always repeatedly use modus ponens to unify with the left hand side and deduce the right hand side. So, what we can do is we can convert the horn sentences to a canonical form and then use generalized modus ponens with unification. We can convert them to implicational form, some left hand side implies right hand side, and then use this modus ponens consistently. So, we will scholemize existential formulas and remove the universal ones. Scholemization means that when you have there exists of some variable, replace that variable with some constant which is not there in the knowledge base, as we did for the potion and as we did for that replacing x by man. Then this gives us a conjunction of clauses that are inserted in the knowledge base, and modus ponens helps us in inferring new clauses. And as we have seen that there are two ways of doing this, one is forward chaining, another is backward chaining. Right. So, what we had here right now was actually a case of what we had in our deduction here was indeed in horn logic. So, if you recall that we started with this one, we scholemized this out and obtained Poisson P and On's Rome P, and thereafter we kept on using modus ponens. So, we unified the left hand side of this rule with this, right, and thereby we were able to deduce the right hand side. Now, the idea is that whatever you deduce on the right hand side will go back into your knowledge base. So, you will see whether you are able to unify the left hand side with what you have in the knowledge base. In this case, we have Poisson P and we have On's Rome P. We have unified that with the left hand side, deduce the right hand side. This goes back into the knowledge base, and then we have hostile Rome, Gall Traitorix and Poisson P in the knowledge base, and these 4 together instantiate the left hand side of this rule, and we are able to deduce criminal X, which we have here. Right. So, in this way, if we have Horn logic, we can continue applying modus ponens to add newer and newer facts into the knowledge base, either through forward chaining or through backward chaining, and we are able to deduce the fact, right. But we will see that this reasoning is not complete, in the sense that there are formulas in first order logic which can be deduced, but cannot be deduced with this kind of inferencing. So, generalized modus ponens is not a complete reasoning procedure, and then in the next lecture we will study a mechanism which is a complete resolution procedure or a complete proof mechanism, right. We will define what I mean by complete, and we will study that in the next lecture. So, let us continue with our study of proof mechanisms in first order logic. So far what we have seen is proof by using generalized modus ponens, which was different from propositional modus ponens in the sense that we had to unify the left hand side of the rules in order to derive the right hand side of the rules. So, we are going to study resolution refutation proofs, which is a complete proof procedure for first order logic. But first we must understand that what is the completeness issue for modus ponens. So, for that let us look at this example. We have for all x px implies qx, right. We also have for all x not px implies rx, right. Then we have for all x qx implies sx and for all x rx implies sx. Now, we should be able to conclude SA from this. Why? Because it is either PA or not PA, right. It is either PA or not PA. So, therefore, it is QA or RA, right. If it is QA, then also we have SA. If it is RA, then also we have SA, right. So, we should be able to deduce SA from this, but we cannot do it by generalized modus ponens, because modus ponens will not observe that this and this, the left hand sides together, cover the entire domain of the predicate, because it is either Px or not Px, right. That this and this together gives us true, the OR of these is not observed by generalized modus ponens, right. And the problem is that this kind of thing, that when you have not Px implies Rx, cannot be converted to Horn form, because we have negation on the left hand side, right. So, here is the generalized resolution rule So, let us study this closely. We are given say two rules which has P1 through Pn1. It implies R1 through Rn2, and we have S1 through Sn3 which gives us Q1 through Qn4. And for some j and for some k, we have unify Pj Qk is theta. So, it means that one of this Pj out here and this Qk out here, they unify, and they unify under the substitution theta, right. So, that is what we do here. So, we have distributed the and over or, and that gives us a set of three clauses. One is not Px or Qx Gx, the second clause is not Px or not of Pfa, third clause is this, right. And then we simplify this is an optional step to obtain this not of Px or Qx Gx as one clause and not of Pfa as the other clause. How do we get this from this? Try to solve it. Take this down as an exercise and just try to see how we deduce this thing from this. It's not difficult. It's just to give you an idea of. It will give you an idea of how to use unification in order to get rid of the third clause. Okay. So, in the next lecture, we will see how we can use resolution refutation with some examples to deduce or to prove certain sentences in first order logic. Yes, the slide please. Thank you.